whatever we older guys tell, it shouldn't have to make the future. So really, thanks a lot that you join and listen. And what I want to start with is to say that most of the slides are already shown once in August this year in a workshop on extra long transnational transmission lines organized by CIGRE in Paris. That workshop didn't only talk about cables, but also about overhead lines, about converter stations, about how to regulate all this kind of stuff. So it was a broader setup, so to say. But today, and this coming half an hour about, and thereafter questions, I want to talk about cables in the settings of long lengths. So, I mean, DC cables in all honor, of course, but we have many, many more kilometers AC cables and AC transmission lines, but let's now focus on the cables. So why not use those? And the simple answer, probably known to all of you, and if not, I will tell you shortly. Cables, being a concentric structure, produce their own reactive power. And if such a device, a cable, produces reactive power, a current will flow through the conductor and, so to say, occupying the conductor with current that cannot be used anymore by useful current, the one that you want to transmit and to use at the other end of the cable. And the graph on the slide shows how this power that you can really use in the end, depends on the length of the transmission line of the cable and also on the voltage of the system. Now this graph is really based on a simple lumped circuit equation that you also can see in the slide. If you would solve the full transmission line equations, you will get the same result, kind of, principally. But what we can learn here, that if you want to transmit really large powers, then you want to use the highest voltage in the AC system. In this graph shown as 420 kV, but it really quickly drops down to, well, in the end to zero when the length increases. If one wants to reach longer, then you go to a lower voltage, but of course then the power is less. And you, of course, can mitigate that by saying, well, I double circuit or triple circuit, but it becomes, of course, very expensive. You see an example of the blue curve, 52 kilovolts, you can reach quite far, but less than 100 megawatt in this example. So the good answer here is, of course, that for the large distances and the high powers, you use DC when you don't have this capacitive production of reactive power. And that's what then the next slide tends to talk about, that this is also quite old knowledge, of course. If you want to reach out for longer distances, you don't use 50 or 60 hertz, you use DC. But of course, still you have losses. The ohmic losses are still the basic ones you have left in your cable system, in the conductor. And if you have a very long cable system, nowadays we're talking about hundreds of kilometers, well, then again, the losses increase. And then there's the old higher voltage technology rule that you say, well, then you go up in voltage, because if you go up in voltage for the same power, you can go down in current, and therefore you have lower losses. And then this graph to the right, in an easy way, tends to show how the cable losses relate to the power that you want to transmit, so the percentage of the power that you want to transmit. And it's one over U curve, an inverse power curve. So you see that it goes really quickly down, but every time you want to decrease the cable losses with another factor of 2, you have kind of to increase the voltage with a factor of 2. And it becomes obviously more difficult the higher you come in voltage. At the moment, we are what I call the sweet spot, is this magical number of 525 kV, which everybody talks about. And again, if we want to reduce the cable losses by a factor of 2, we have to go to the double of that, which is 1050 kV, which is far off what we can do today. So probably and provenly, if you look at all the commercial projects ongoing, we are living with 525 kV for the next couple of years, which is good enough, I would say. And the kind of loss we're talking about at this voltage is about 0.3% cable loss per 100 kilometers. And just to give an example, what you can reach if you, from the center of these circles on the map here, with a 3% loss, which is not that strange, you could reach and bridge 1,000 kilometers. Well, this presentation originated from CIGRE in Paris, so we had Paris as a center. And you see that you can reach northern Spain or Denmark, Austria, Ireland. And if you increase the acceptable losses by just pick and choose, like to 4.5% and then later 6%, you increase to 1,500 and to 1,000 kilometers, kind of roughly. And then obviously you can reach really long distances. And I want just to remind you that already when I started as a young engineer in 92, 93, one of my first assignments was to participate in a study in the Netherlands to look at the feasibility of a cable link between Iceland and at that time the Netherlands. Well, it seemed to be at that time feasible, or it was bankable, it was technically feasible, but it was not performed at that time. And the ICE link has repeated itself in kind of feasibility study every, I would say, 5th year in different shapes. Iceland and Netherlands, Iceland, Norway, Iceland, Scotland. Still not done, but who knows, maybe in the next coming decennium, it might happen sometime, who knows. What you also can do as an example here, and what you can learn about this graph, is to put all the commercial projects that have been installed and are being installed, manufactured in a graph, which relates to the U0, the voltage of the cable system, and related to the project core length, which is often with bipoles just a double of the transmission length. And then you see, well, it's not a perfect correlation, obviously, but you see a kind of arrow that points in the top right corner. And indeed, it was true, because when, for about 10 years ago, the voltage 300 and 350 kV was introduced, all the projects all of a sudden happened at that voltage. And since we introduced 525 kV, now all new projects, also the ones that are ahead of us, they talk about 525. So we are always heading for the highest powers and the highest voltages. And well, as I explained earlier, DC is about larger distances. So simply, when you talk about DC, the very existence of the reason of existence of DC is to have high powers and larger voltage and larger lengths. So you automatically end up in the top right corner. That is maybe not so strange, but what does that tell us? Well, that tells us that when you operate at the highest voltage and kind of 2 gigawatt transmission power regime, the consequences of an outage are far more serious than if it is a 100 megawatt link, and maybe one city gets dark, a smaller city. But if 2 gigawatts falls away, then the whole region, or if you take into account cascade effects, maybe half of Sweden, in my example, where I live, would turn black. And we have, in the last 10, 20 years, seen major blackouts that are an effect of cascading effects. And this could happen if you talk about major, important, high-profile links. This is combined with the inherently long distances, large project core lengths per project, meaning large project execution complexity, because it's not that easy to design, manufacture, produce, install 1,000 kilometers of cables. So many things can go wrong. So when you say DC, you say inherently large project complexity and large outage consequences. In other words, you have to have very, very good control on everything you do, from design to production, transport and installation. Quality assurance is of key importance here. Now, what are some key aspects that we can see when we talk about DC cable systems, and what are the trends? Well, I've obviously talked already about high voltage. I also said to you already that the current industry practice and the sweet spot also in terms of not taking too big risks and too big steps and having enough power for the moment is 525 kV. Recently, I saw a new announcement of a cable manufacturer that has qualified their system for subsea use, using a somewhat higher operating temperature and stating that they can reach 2.5 gigawatts. We also know that there is at least one cable system that I know of in service at 600 kV. It uses PPLP technology. I also know one manufacturer having fully qualified by PQ test and type test at the 640 kV level. So 525 is the sweet spot, but there are some, some signs of already increasing voltages. The typical classes of cables, DC cables that do exist at the moment are, well, first divided into two categories that are the extruded technologies. See 3 examples on top, and the so-called lapped technologies, where you lap 100-200 layers of tape around the cable core, the bottom 2 pictures. If we start with the bottom 2 pictures, they were, by the way, the first that came into existence, or at least the MI cable. MI stands for mass impregnated. So all these numerous paper layers are impregnated with a high viscous compound. I don't say oil, it's more like kind of a honey-like, very thick compound. If you cut that cable, nothing will drop out almost. Has been introduced in the early 50s, so it's along already for more than 70 years. Much later, PPLP, which is polypropylene lapped paper tape, where the purely paper tapes were interchanged or exchanged with a laminate of polypropylene and paper, has been used, well, quite a lot for AC, but not that much at all for DC. So these are the lab technologies, but we see an enormous increase since the very beginning of the extruded technologies, which come currently into 3 flavors, baptized as DC XLPE, XLPE standing for cross-linked polyethylene, well known from the AC world. Another one, which is the nano-filled compound, at the moment commercially nano-filled XLP. And then the third one, which is with the acronym of HPTE, high performance thermoplastic elastomer, or in short, thermoplastics. It's also commercially available at the moment, at least by one manufacturer. It has not been used in the beginning of the AC extruded era in the beginning of the 60s due to reasons of mechanical stability and high temperature performance, but that has been solved, and who knows what happens in the future. But anyhow, these are the 3 classes that exist today, and the question could be for the future: will we see new classes and new innovative materials? Maybe I will discuss that a little bit later, but we have to understand that it's not only one kind of performance in the laboratory that we're seeking for. Sometimes I read an article that there is a new material that has the very best performance on low conductivity or low space charge accumulation. That's very nice, but to be an industrial material, that means that has to be good, of course, but also the temperature performance, the cost, the availability, the volume, the transport, the quality assurance, all that kind of the diamond all these facets are needed to make it a good material for the industry. But in future, I'm sure that we will see, when we leave the sweet spot of 555 kV, higher voltages, which will need higher field strengths, and which come also with an extreme need for cleanliness, not only physical cleanliness, but also chemical cleanliness. In terms of, if you talk about AC cables, we are always afraid of protrusions and dust particles or metal particles inside the insulation, which will create field enhancement. That is dangerous for AC cables. That is also dangerous for DC cables. But on top of that, we know that the dielectrical properties of DC compound is very much depending on the molecules inside that define the space charge behavior, the local conductivity, etc. So if you know what chemicals should be inside, you want to keep everything else outside. So chemical cleanliness is also important for DC compounds. Now, another way of course, increasing the power is to increase the current. And that can be done in two principal ways. Either you go for larger cross sections, or you go for higher operating temperatures, keeping the same cross section. And I see a trend in both directions. We have been using cross sections like in both AC and DC, like 2,000, 2,500 square millimeters as a maximum practically, with the one and other exception. But now we see a trend that 3,000 is being used quite often. It's used in the corridor projects and in Germany, and that are large lengths. And we also get articles and publications that manufacturers are going beyond that, beyond 3,000 square millimeters. Now, of course, there is a limitation, both what the manufacturer, the factory can handle, the mechanical properties, how you could still bend the cable or the weight. So I don't think we will see figures like well above 4,000 square millimeters, although I'd still put into the graph here. But an increase above 3,000, I think we could see. And you also see in this graph the rough estimate, and these are based on the simple designs of a submarine cable, single armored estimates. The weights become, of course, very high if it goes to a non-existing extreme of 5,000 square millimeters. I talk about 80 kilograms of cable per core, not a double cable, not a double core, but one core. It's quite some stuff. And therefore, it's important that to realize that aluminum, although less good conducting material, therefore less power for a cross section, it has an advantage of lower weight, and definitely also of lower price, although the price levels are fluctuating like never before at the moment. But typically, aluminum has been at least 3 times cheaper the last 10, 20 years than copper. If you go further back in history, it was almost equal. But if it is cheaper significantly, then aluminum is a good example to use. Another trend we see is that we ask for larger depths, cables to be laid at larger depths. We talk about subsea cables, obviously here, not underground cables in this example. Mediterranean, very nice area, but it becomes extremely deep at many places. There's one example of an Italian manufactured cable, the SAPE cable, Sardinia, Italy mainland, which goes down to 1,640 meters. I think it's the deepest so far. And you could say, well, but it sounds nice, but already for many years back, and you can see it on the screen here, 1858, we had a transatlantic telegraph cable, copper wires at the time, no optical fibers, of course, and it was at I think the maximum 6 kilometers, but at least if you read the papers, it's more than 4 kilometers along the length, which is extremely deep, not being performed with power cables. But the simple answer is that that cable weighed 0.5 kilogram per meter. And if you remember my previous slide, we talked about 50, 60, 70, kilograms per meters. And the key thing about installation of cables is about mechanical tension. If the cable is being laid from the vessel, the installation vessel, to the bottom of the sea, the catenary, the length of the cable hanging from the vessel, becomes, of course, equally longer when the depth increases, and then the tension becomes also linearly larger. And if the cable already weighs more per meter, then the cable must carry its own weight. And now we are talking about many tons of cable that has to be carried by the cable itself and by the vessel. So that is one of the bigger challenges of laying a cable and at large depths. But it's not only that. People sometimes only focus on the tension during the installation of the cable, and we think about armor wires. And of course, armor wires are very important, but in a typical cable, the mechanical forces are divided, not equally, but 30, 70%, 40, 60%, depends on the design, between the armoring and the other metal component, which is the conductor. So your conductor connector and the conductor itself, but the conductor joint is the weakest part, has also to be very strong, and increasingly strong if you go for larger depths. Joints themselves, maybe if the field joint or the repair joint has to be able to withstand all these large forces. So we go from one regime, voltage, current, field stresses, molecules, to mechanics, which is just as important if you want to tackle the larger depths. Lately, a company in Europe has got not a contract yet, but the preferred supplier they have become for a cable in the Mediterranean with a maximum depth of 3,000 meters. Congratulations for that, not being done yet, but that's a big challenge, and it will be very nice to see when that happens. So things change. Next topic, which I already touched upon as the raison d'être, the very reason why these exists, is larger distances. But that has an effect on the logistics, as I talked also about. Was one of my first project managers when I was a young engineer. He said, "Mark, forget everything about high voltage. Indeed interesting, but we are dealing with logistics here." Well, that was, of course, his perspective. But I always took these words with me, and the older I get, the more I appreciate that is indeed a big part of projects which we as technology engineers have to appreciate and to understand how that fits into the bigger picture. Now, for submarine cables, we talk about large delivery lengths at the moment. So the largest lengths that can be transported on one vessel obviously depends on the cable size, but we are talking about 100 kilometers or more. So we are in that range. We are talking about future projects that talk about future vessels well above that number, maybe 140 kilometers, 150 kilometers. A huge amounts of cable. That means that the storage turntables, where you see a picture of that, have to be much larger. Controlling that weight, we're talking about 10,000-ish tons of cable that has to be controlled when it turns. Think about that. It's a completely different topic than what I'm, dealing with, like, high voltage, but it's very important. For the underground cables, typically the transmission system operators say, we do not want so much field joints, because joints are still seen as the weaker point of a transmission system. So the lesser joints, dear manufacturer, the better. So the technology there has nothing to do with, again, high voltage. It's just transport and the logistics. What is the maximum length I can transport on a drum on the roads in a certain country? That is the size of your truck, and that is the weight. And then at the moment, we typically are at 2-kilometer kind of lengths of the largest cable sizes. And then we talk about 100 tons that are transported by road. So my main message here is that we have to understand the challenges of transport and logistics, even if we are maybe high voltage engineers or we deal with chemicals or other stuff. It's part of the story and it's just as important. Now, testing is, of course, another topic that becomes more and more important for different reasons. The first reason is just what we call for qualification testing. If you take one step back, the category of testings are, you can divide it into many bits and pieces, but you could say we have qualification testing, we have testing during manufacturing, and we have after installation testing. Now, qualification testing is something we do hopefully only once for your new technology or only once for a project. And you do it on shorter pieces of cable and a few accessories, joint terminations. It's regulated in IEC documents, in IEEE documents, by the way, as well, in CIGRE recommendations. And the two ones that are very much important are called pre-qualification test and type test. Now, the pre-qualification test is something that you do only once, and you test the technology. In the type test, there normally you qualify the chosen solution, the technique. Now, what I think in future will happen is that instead of all the time asking for this new PQ test and type test, one might make use of the range of approval, meaning I, as a manufacturer, could say, I have already done my type test 2 years ago, another project. There's the same kind of cross-section and voltage rate. Can I use that in your project, dear customer, within the range of approval? I think it would help the industry if we, in an, of course, very responsible way, use that tool of range of approval to not see a further explosion of testing. Testing will be part, it is important, but you have to be careful to not overdo it. It's a very delicate balance, I can say. Now, the other one is manufacturing. That means that every single meter of cable will be tested in some way. And every single accessory joint termination will be tested before leaving the factory. And one aspect I want to lift out here is the trend we see in submarine cables. Manufacturing lengths becoming larger. So in length, I mean here, delivery lengths I just talked about becoming larger in length as well, means that if we test these lengths, even being a DC cable, with AC, because AC is still seen as a better tool, as a voltage to detect failures and issues with the cable, means that I need a huge series resonance test sets to be able to test these many kilometers of cable. And if I now tell you in future we are maybe leaving the sweet spot of 525 kV and go to 600 kV or maybe even 700, who knows where it ends, then the AC testing volts would also increase. And if the lengths also increase, we come to a point where the series resonance test sets become incredibly large. And I will not say it's impossible, but it becomes large at least, and we have to at least think if it should continue or not. And then we have the after installation. What one cannot do anymore is to put an AC voltage on the whole cable link of maybe 500 kilometers. There is no mobile test set that can put this kind of voltage on this long cable, which will ask for the reactive power. One can do so, and it is being done and discussed on shorter sections at length. And there the trend is also disturbing if you look in the future. If you look at larger lengths and higher voltages, even that will become a challenge. At the moment, I think it's necessary because we never have had this top level voltage in the cable systems, 555 kV. But maybe in future, when we get used to it and see the performance during after installation testing, we might say that the AC and PD testing is maybe not necessary anymore. But it's a careful balance. At the moment, I think it is necessary. In the future, we have to balance what is possible and what is necessary. But the future is the future. I just want quickly to mention only for you, not going into too long detail here, is that many cable systems, if not all, are using integrated fiber optics. So one armor wire or maybe a copper screen wire in terms of the underground cable is removed and replaced by a fiber optic in metallic tube. And one can use the sensitivity of these fibers to temperature and strains in order so to detect the temperature in a distributive manner along the cable and even to listen, acoustic sensing, on what is happening along the cable, which can be very useful when you have a failure in the cable. You want to detect the fault. So the breakdown will, of course, make sound. You can listen at the end of one fiber and locate where the error is. The limitations are still the length, but it will be improved as anything will be improved in future. Now, something that is very important, which I want to mention here is, which I want to again mention here, is the necessity of quality assurance and quality control of especially DC cable systems, because as I said, the projects become longer and the outage consequences are large. So it better not happen. TSOs, and in the end, you and me, want still to have the highest availability and reliability. And that means then that the failure rate per kilometer that we could accept must go down. If I double the length of the transmission line, I would all of a sudden request half the failure rate to have in the end the same availability. And there are sometimes debates stating, well, that won't be possible, because if I look at the failure rates, the historical failure rates, which are documented in CIGRE documents, then you see it will not happen because they are too high. And then I want to stress to all of you that, well, that's true, but these are historical data, which of course tell you something. It tells you at least we have to become better, but we are the people that make the failure rates or not. We are the ones that make the cable systems in a quality controlled manner or not. So the failure rate is not a constant of nature. It's something that we define. So the length that is possible with a given availability is up to us, not to somebody else. But if it happens, if a fault happens, it must be located. Where is it? It must be repaired. And the two important messages here are that the nowadays accuracy of fault localization, which is by the way, in two steps. You do first a coarse localization and then a fine tuning. And the first step, this coarse localization, has typically an accuracy of about 1%. And if I talk about future increasing lengths again, say I have a transmission line of 1,000 kilometers. Well, then it's 10 kilometers, my first estimate, which is still quite some length. So it would be very nice in future to have fault localization methods that have maybe 0.1% accuracy, or even better. And I think mathematical modeling is one of the topics that can help here. The other topic is to have a repair preparedness. This is, again, kind of the logistics of the story. Once you have a fault in your system, a failure, and you have located, it's better that you are prepared with the repair joint, with an extra length of cable, with your vessel, with your crew, so that you can repair as quickly as possible and not wait several weeks to gather all the stuff. Simple, but very important. So what will we see in future? Again, I don't repeat this one, but I only want to add that we have seen few reports in the laboratory of extreme values of 700 and 800 kV as a U0. So the test will be the multiple of that test voltage. I do think we will live with 525 the next, say, 5 to 10 years. I even hope so, because the challenges are enough. But the future might be even higher. Higher current, we will see it. Larger cross sections, I do think we will talk about 4,000 square millimeters. I do think it will be maybe be a little bit more if we talk about aluminum. I do think we will see more aluminum, certainly for the larger depths, by the way. What would be the biggest dream of the high voltage technology, where we haven't seen any progress, we're still living with copper and aluminum, would be a new kind of solution, a new kind of low loss conducting material. It was a dream for 10, 20 years back when we introduced graphene, that we could have some kind of very low loss based materials, but we still haven't seen it. But I think there is work ongoing in laboratories, and well, who knows? Who knows? Oh yeah, well, the other message I wanted to give you here is, if all that higher voltages and higher current would lead to 3, 4, or 5, who knows, 6 gigawatts, the question is also to the TSOs, do we really want that? Because then you come to the consequence of an outage. Can the grid take care of a loss of 5 gigawatts? So without a grid that can take care of that, there is no need. Larger depths, I have already mentioned for you that 3,000 meter is a project which will be executed. Well, at least there's a preferred supplier. It is also has been reported as doable. Then the next question should be, is there a need for even depths beyond that? Well, my first reaction would be, hold your horses. Let's first do 3,000. But also an old dream of some people, which I could challenge, but to lay cables across the Atlantic. Well, if one does so, which one can challenge, one would need depths far beyond that. And again, I state it's not only about the armor, it's the complete package that has to be thought about when you develop cable systems for these depths. It's the joints, the recovery, the repair, the stresses in all the components, the sidewall pressures, contact loads. So it's lots of mechanics which goes in there. On the length of the transmission lengths, we have already seen now, I would say, the corridor projects in Germany, of which the longest is now 750 kilometers, I think, the Südlink. It's an extreme length. We have already some submarine cables also between Norway and England. The Viking link, we're talking about 600-700 kilometers. So we are there. But will we see the 1,000+ kilometer lengths? I've talked already in the beginning about this recurring ice link. We can read on the internet about some cable projects between Australia and Singapore. Some people say it's madness. Other people say it's not madness. Maybe it's going to happen. We learn about the X-Links project between UK and Morocco. Some people say again it's madness. Some people say it will happen. Who knows? But one thing is clear. We will need extreme QA and QC to get this failure rate down to achieve these lengths. And in testing, well, I've already told you about the challenges of HVAC testing in the factory. We'll see what will happen. Another way is, of course, to go down in frequency. Then, of course, the charging current becomes automatically less. It goes linearly. So you could use maybe frequencies below 10 hertz, which is still accepted. VLF standing for very low frequency, going down to 1 hertz or below. You can talk long about that, but it's a possibility. DUC, which is damped AC testing, highly debated in different communities, but it could be a possibility. Who knows? I don't answer here. I just put it up as a possibility. And the old dream of many, will DC, partial discharge detection, finally enter the scene? I know the work is being done. The challenges are there because the frequency of occurrence of such PDs are far less than under AC. But we have really, really advanced computer technologies here. Maybe we could learn from other science fields to make this really happen. Who knows? And at last, I think also we absolutely need quality assurance to step up. As good as we are, we need to become even better and think about not only doing more of the things we already do, but doing new things. One particular example here, which I mentioned, is the acoustic detection in cables and factory joints. And when maybe the electrical testing becomes more and more difficult due to this huge equipment, then acoustic detection in factory joint, which is a local joint, could be an option. And maybe there are other things that can become better. Also, the soft topics like poor communication across interfaces in different phases of a project. Don't underestimate these kind of issues, which is also important. I hope really that we can come to technologies and solutions that can go beyond this 1% of fault localization accuracy, 1 promille, 0.1% or even less. I do think it's possible, and I see too little research there. It would be great to see something happening there. Something which the European Union is screaming for is shorter project times. And if we want to reach the climate targets in 2030 and 2050, and all the projects that are needed, this will not happen if the project times are equal to those we have now, which takes sometimes 10 years or more from start to end. We have to shorten the permit processes. That's far out of our hands, and I know many things are happening, but it's important. I think also what is needed is that the tender processes, the whole discussion between manufacturer and the buyer, the TSO, that wants to buy a cable system, that whole process can also be, I think, streamlined more and shortened. And then again, what I mentioned earlier, should we maybe make more use of range of approval, not too often do a pre-qualification test, which takes about 1.5 years, including the build-up of the whole system. This is not a way of stating, let's forget about QA, QC. That must always be at the same level and even better. But it's still something that we should think about. And then last but not least, nothing will happen in future with people like me, which will target for 60 years of age. It's about young people, young professionals like all of you. You're absolutely the future, and I said it at CIGRE I think it was last year, that the future is in your hand, and you have the responsibility even to come up with ideas. And we that have been long in the business shall not say, oh, we have done it already, it didn't work. We shall support. So our role is support, and your idea is to take the lead and step forward. That is really what I want to imprint in all of your minds. You are needed quite a lot. And this is the last slide in my presentation. It took some more time than I intended, but I hope it was interesting.
All right, thank you so much, Marc, for the nice presentation. So we got 10 more minutes. If there is any question from the audience, we will accept. I think I saw one question on the chat box. Question to Marc: in terms of new cable insulation material, do you have a view on whether better dielectric strength or better thermal conductivity would be of more value?
You talked about thermal conductivity, or? Sorry,
yeah, the question is posted on the chat, but I can read it. In terms of new cable insulating materials, do you have a view on whether better dielectric strength or better thermal conductivity would be of more value?
Yeah, I think what is more needed, well, both of course is interesting, but I would rather see dielectric strength than thermal conductivity. If I compare that to where we are today with XLPE, XLPE has a certain thermal conductivity. I don't have the number in my head. You probably have. Polypropylene is worse. It insulates more. But I think if we're going for larger, higher voltages in future, dielectric strength is of course something would be very much needed, because for the simple reason, if I go to higher voltages, I probably want to keep my cable size in limits. Therefore, I need a higher field strength. And if I don't want to have a very little margin from the operating field strength to the breakdown field strength, I better increase the dielectric field strength. So I would go for that one.
Okay.
The chat as well.
Asked unmute. Mark, you can go ahead and I unmute you so you can speak.
Thank you, Matteo. Thank you very much, Marek Jeroense. Mark, great presentation, really a lot of topics, and especially this future-oriented hints very valuable from your experience. My question is, you showed at the beginning the map of the telecom cable from the mid of 19th century. It was very interesting. If we would right now map such a map of HVDC cables with these mass impregnated cables, polypropylene, probably thermoplast cables, my question is, what is the average lifetime in those classes? Does what you have installed based, and what is your thinking in this context? And the second part of the question is there any difference in lifetime between the cables with the conductor made of aluminum or copper? Thank you.
Thank you. Well, the typical lifetime that is contracted, which is maybe not the same as what we know, but it's 40 years for interconnectors. Cables that are connected to wind farms, they have an economical lifetime of, say, 20, 25 years, somewhat shorter. But for typical interconnectors, we say it has at least to survive 40 years. If you look back, we do not see typical signs of aging such that DC cables tend to stop living after 40 years. Mostly if we're in good shape and health and no environmental changes are there, they typically can live and survive longer than that. It's of course difficult to say of the future cables because they have stepped up in both voltage and temperature and I don't know what new materials. But the expectation is that it will at least be 40 years as well. Aluminum versus copper in terms of life length, I don't think there is any difference as long as, of course, the cable is watertight, which it should be anyhow, otherwise it will break down for other reasons. So if water does not enter into the conductor, again, which it will not, I don't see any difference in lifetime for copper or aluminum.
Okay, so here is no difference. And in terms of the space charge, do you see the space charge to be a serious problem in the future?
Well, space charge is an interesting topic that would need a long time of discussion. It will always be part of the design process. It will always be part of the R&D, which it shall be. First, I want to say space charge as is nothing strange. It is something that Maxwell equations already predict. as soon as you have two materials in connection with each other with different properties, being EPDM and XLP, or silicon on or XLP, on the interface you will per definition have space charges. In addition, if there is a temperature drop across whatever material, you will have a distribution of conductivities due to the temperature dependence, and then you automatically will have space charge. So at first, I want to give the message: we have to accept that space charge in one way is something that is nothing strange, and that is something we should just accept because it's what is predicted by the Maxwell equations. That having said, means that we have to understand the basic properties of the materials to be able to control the space charges. Once we understand the conductivity and we can describe it by measurement, how it depends on the temperature and how it depends on the electrical field, in that way we can then control it. Another way how space charges are I will not say created, but affected is by the chemical composition of the materials. So again, if we know the chemical composition and we know how things move around in the XLP or in the EPDM, then we know where the space charges will be, and then we control them. So in that sense, yes, it will always be part of the design process. It shall be. But it's nothing mysterious, I would say. It's something that we could understand.
Thank you very much.
All right, maybe last question, Marc. How the operational scenarios such as polarity reversal will affect the cable reliability?
Yeah. So there are two converter station types. Well, on a high level, voltage source converters, which change the direction of the power flow by changing the current flow, but not the polarity. And the line commutated converters, which does the other way around, keep the direction of the power of the current in the same way, but change the polarity. Is always a bigger challenge from the electric perspective or for the cable when you do it with the LCC, with the polarity reversal. There are a number of companies that have qualified their cable systems under an LCC regime with polarity reversals. It is more challenging. What we see is a gradually increase in the use of VSC technology, not using voltage polarity changes. Therefore, there is less need, if I look ahead, for these kind of materials, or this kind of behavior, I would say. LCC is so far only used for the extreme, mostly, for the extreme cases, like in China and India, when we talk about 6, 7, 8, 9, 10, 12 gigawatts of power transmission at 800,000, 1100 kV. But at 525 kV cable systems, we are already talking about VSC components, converter stations, where we do not have the polarity reversals. So it might become a non-issue in future. All of the qualifications ongoing, I cannot say all, but many are in the VSC regime, not doing polarity reversals.
All right. It's almost time to finish the webinar. We got a couple of questions, but I share Marc's email so you can reach out to him. So with this, I thank the speaker. Thank you so much, Marc. And that's the conclusion of the webinar. Thanks for joining.
Yeah.
All right. Bye-bye.
Thank you.